Piston project presentation. We know that some of you might just jumping from that meeting, and we thank you to come early to our weekly seminar. As you can see, we have speakers in subsequent weeks, and please come to attend the next week's seminars as well. Today, we are privileged to have Roy Fox from University of California at Irvine. Roy obtained his PhD from Hebrew University, and after doing his postdoc at UC Berkeley, he joined UCI, where currently he's doing research on theory and application of reinforcement learning, algorithmic game theory, information theory, and robotics. His current recent focus has been on structure, exploration, and optimization in deep reinforcement learning and limitation learning of virtual and physical agents and multi-agent systems. Today, we are going to listen to his talk on population-based methods for single and multi-agent reinforcement learning. This is an area of interest in both multi-agent and RL and /ML communities, and we hope to learn about this topic more today. With that being said, I leave the stage to Roy.
Yeah, thank you, and thanks for the kind introduction and invitation. Let me try to share my screen. Do you see it?
Yes.
Great, thank you. Yeah, so very excited to talk to you today. I'll briefly give an intro to reinforcement learning, just in case not everyone is up to speed on it. Just at a very high level, we have an agent interacting with the environment, and you've probably heard about this from many recent successes. It's hyped to some degree, but also very exciting applications coming up. Visual navigation, potentially for robotics, all kinds of virtual application, infrastructure management, and so on that are actually being deployed today. And hopefully one day, real robotics with dexterous manipulation and all kinds of object manipulation and navigation and so on. And you've probably also heard of reinforcement learning from human feedback for fine-tuning large language models recently in the news. So a lot of really exciting applications, and we're really going to go back to the foundations of the very basic algorithms and see if we can say something even very simple that makes a big impact. So an environment is essentially a state that evolves over time, and there's an agent that can control that evolution of the state through dynamics. So this next state distribution depends on the current state and the agent's action. And the agent's action is decided by a policy that decides the action given the state. And then the agent gets a reward for taking such an action. And what do we want? We want high rewards. When do we want them? As soon as possible. So our objective is going to be to maximize the sum, average, weighted average of rewards, where future rewards are discounted exponentially by this discount factor. And it's the expectation of this return that we're trying to maximize over agent policies. So that's in a nutshell, reinforcement learning. And please let me know in the chat if anything is unclear. Happy to take any questions. On the basic algorithms in this field is called deep Q learning. It goes basically like this. So we can define a Q function, which tells us for a given state, and any action doesn't need to be the actual action that we're going to take. It could be a counterfactual action. What is the expected future return given that we do take this action in this state? And so we can maybe approximate this function, this Q function, with a neural network that takes in a state as input and outputs a vector of length, the number of actions, with the Q value for every action. And so if we have experience, a state, an action taken in it, the following state, and the reward obtained for it, then we can try to come up with a better guess for our Q value. And that's the one step expanded value, the first reward plus the discount times the maximum of the reward that we would get in the following state. And so this right-hand side is a better guess for what the value is. So let's make a loss out of it. For gradient-based optimization, we take the square difference between the sides of this equation, and we're trying to minimize that loss. There's a subtlety here that I'm going to talk more about in the next slide, that this term here has a slightly different network, which is called a target network. We'll talk about it more in the next slide. And so now if we have this Q function represented in a neural network, we can find the policy. It's just, if we have the value for every action, let's just pick the best action. That's called the greedy policy. And that's a policy we use. So that target network, why use it? Just as a reminder, this is the DQN loss, and the term here is coming from a target network. One effect is that there's no gradient through it when we take the gradient over theta. And that's good because these terms are our target. We're optimizing this term. So that's a good thing, but also the target network is a lagging copy of our learner network Q, right? So here's the learner network, here's the target network, and it's a lagging copy that is being updated slowly, maybe exponential, with an exponential window. That's one common way to update it. And the effect of that is that it stabilizes the learning process, right? So this target network is less sensitive to data just because it is updated less frequently, to a lesser extent. And so it has less variance inside learning run, and so it's more stable. However, it does incur bias because if we're using for the target not our best estimate for the Q value, but some lagging copy of it, then it has bias. It's not the best guess, it's biased. So that's a trade-off, and in practice, we often, or almost always, need to have this trade-off, otherwise the process is just not stable enough. So already you see a hint that what we're going to do is reduce variance enough that we don't need the target network. But actually, there's a lot more value in reducing the variance. Generally, in machine learning, variance is bad. In reinforcement learning, it's no exception. It hinders learning through several ways, right? So first of all, if we have variance in our Q value estimate, then we're taking the greedy policy. We might be taking the wrong action, right? So a suboptimal action may appear optimal, maybe the greedy action, even though it's not optimal, and then we take the wrong one. So that's not good. Also, it can cause instability of the learning process. So when we talk about variance, we talk about variance across training runs, but it also creates instability inside a training run, right? More sensitivity to the specific sampling of our data, of our experience, means instability within run. States that should appear similar appear dissimilar, and that confuses our learning. A lagging target network can stabilize it, but again, is biased, so that's not good. And there's a third reason to reduce variance, which is that it is related to what we call the Jensen gap. So the Jensen inequality says that if you have a convex function, it overestimates the expectation essentially, and a maximum is like that. So if we take the maximum of a noisy Q function, it overestimates the real expectation, the maximum of the real expectation, right? So that's sometimes called the winner's curse, right? If a noisy evaluation is a winner, it tends to overestimate, and therefore we tend to be disappointed when we learn the real value. And so in Q learning, because of this, right, for the target, right, we have that variance induces bias in our learning. So that's another way in which variance is bad. And indeed, we see this is already a sneak peek of our results later, that we see that the variance measured here across runs is correlated in terms of which kinds of methods are higher or lower. It's correlated with this Jensen gap, this difference between what we have and what we would like to have in our target evaluations. Generally speaking, the lower the variance, the lower the gap, so the lower the bias introduced by this target. All right, so how to reduce variance? There's many ways. Generally in machine learning, one of the most successful ways of reducing variance is to just use many models, use an ensemble. Methods such as bagging, just averaging over a large number of models, and that reduces variance to the extent that these models are uncorrelated. In reinforcement learning, ensemble methods have been used before, but never quite for this same reason. So double Q learning and deep double Q learning have used an ensemble of size 2 to reduce this bias of the target due to the Jensen inequality, but not by just averaging these models, but instead by taking the argmax action from one estimator to evaluate the other estimator, in this case, the target network. And that introduces provably a negative bias that just seems empirically to not be as bad as the positive bias that we get in usual DQN. Max MeanQ generalizes this to more than 2 network models in your ensemble. You take the minimum over some M number of networks and before you maximize over actions. And that decreases the bias the larger the ensemble, the more models you minimize over. At some point it crosses 0. We don't really know where it is, but being slightly negative turns out not to be too bad. So that's a good method. And finally, ensemble methods have been used for exploration separately from the optimization target that these methods use, but just for exploration, how to sample more data. We would like, generally speaking, to prefer experience that we are more uncertain about. So if it has high variance in our ensemble, maybe we would like to prefer those states. And so upper confidence bound exploration gives an exploration bonus to those states where our ensemble has high variance of the value prediction. Sunrise is a pretty recent method, pretty powerful one, where again, the ensemble is used inside the optimization to downweight the updates, the gradient updates that have high variance targets. So we're less sure about them. We're going to downweight them, and we combine that with using the exploration. So those are really powerful ensemble methods, but none of them are really touching what classic machine learning does with ensembles. So can we do just that? There has been works that tried this: ensemble DQN, ensemble bootstrap Q learning. Those methods train all ensemble members with the same experience. We will see that this is not a good design choice. Average DQN averages past snapshots of the same learner. Already in this original paper, it is less as effective as ensemble DQN. Those methods have the same motivation of just using a classic ensemble, averaging the targets for learning, but subtle design choices make them not as good. So let's see what does work. It's a really simple method, actually, just with careful design. So we call this method MeanQ, and the idea is to learn an ensemble of value estimates Q theta k, where k runs from 1 to big K, and they're all trying to estimate this expected return. And so there's going to be an ensemble here, and there's optionally going to be an ensemble of target networks. Later, we're going to do without them. And we're just going to use the ensemble mean for everything that we would use the model itself in targets and in the policy. So we use the ensemble mean for the target and to compute a loss for each member of the ensemble. And then we use the ensemble mean for the argmax of the greedy policy, use that for exploration to collect more data. We sample from this replay buffer of exploration data to train the ensemble and in a lagging way copy it to the target. So it's a very simple method, really. But let's see the design choices that lead to it working so well. So the first choice is that our exploration policy is actually going to be shared. It's going to be the same for all members of this ensemble, right? So it's going to be this argmax of the mean, regardless. It's not like every policy is exploring for its own experience, which would be the case with approaches sometimes called deep exploration, where we have an ensemble of policies, each doing their own exploration, each doing an entire episode of interaction with the environment to collect more consistent episodes where the actions are consistent throughout the episode. That is shown to be useful, and we think it would actually be useful here as well, if not for the mismatch that this would cause between the data we collect and the policy that we eventually deploy. So that mismatch turns out to be more important than having deep exploration. So we're matching our deployment policy for exploration by having this shared exploration policy. The second design choice is that we collect all this data to a shared replay buffer. Again, we could have maybe the same exploration policy, but collecting data into separate replay buffers. And the intuition here is that, why have a replay buffer in the first place? The idea is that it diversifies the experience that we have. And so by just having one big joint replay buffer, we keep that diversity of the data. However, we sample from that buffer independently for every ensemble member. That is a key difference from some of the past methods, and that turned out to be really important because that maintains ensemble diversity, which is important for the averaging to reduce variance. And of course, we can combine this method with existing methods, which hasn't been done before. There's some subtlety in rainbow techniques, specifically for distributional RL. There's some subtlety how it interacts with the ensemble, but nothing too crazy. Let's go quickly through them. So rainbow techniques is trivial to combine with dueling nets, with noisy exploration, with multi-step targets. We don't actually use multi-step targets. We found that the hyperparameter should be actually just a single step optimally for this case. For prioritized replay, we found that it's important for the prioritization to be individual for each member as well. And then for distributional RL, there's a subtlety in how to combine them, but again, I won't go through the math, but it's what you would expect if you think about it carefully. And then double Q learning, which is one of the rainbow techniques, is actually splitting the ensemble into two, so we don't do that. That would have our ensemble size, so we don't combine that method. But also it's made a little bit redundant because the bias is reduced by reducing the variance and therefore the instant gap. And we combine this with the UCB exploration. As long as we already have the ensemble, why not also improve our exploration? Essentially, we add this term, which is an exploration bonus for when our ensemble has large standard deviation of the value estimates. It sort of drives curiosity about states of which we're not sure about the value. All right, so let's see some results. Because it's kind of surprising, right, that such a simple method the space has been explored before in a lot of prior work, and we can have this exact choice of design considerations that just works very well. So let's see how well. So we tried this on the Atari benchmark. These are video games that are a popular benchmark. There's a subset of 26 games that are often studied because they don't require as much exploration. They don't require as much memory because they're not so partially observable. And so we focused on that subset, and we see that we outperform on many of these games past methods after 100,000 interaction steps with the environment. On average, we really outperform them by a large margin. These lines are what happens at the 100K, and the blue curve is how our method improves towards the 100K. At 500K, we can compare to more methods where we did not have the baseline values for 100K. The interesting thing to notice here is that this is normalized to human performance. So 0 is random and 1 is human performance. So our method overtakes human performance at about 200,000 interaction steps across those 26 games, plus minus 100,000, which is kind of cool. Probably record setting. We can dive a little bit deeper to understand what exactly is going on. So here we plot the return for 3 games. And we see that our method in red without a target network outperforms the same method in green with a target network, whereas the baseline DQN really does need the target network. Without the target network in orange, it doesn't go anywhere. With it in blue, it does get somewhere. So it really does require the target network. For us, because we reduce the variance, as we can see in the third row, because we generally tend to reduce the variance, we don't need the target network, and that also reduces the bias that the target network introduces. For the baseline DQN, the variance is so high that the bias that is caused by the instant gap is just off the charts for the orange method. And this is averaged over the four of the environments. Okay.
Quick question.
Yes.
So when you do these experiments, do you start from the same initial point? I mean, in terms of initializing the weights for your network.
Yeah, so you're asking if it's a random initialization or if it's the same random initialization?
Yes, the same random initialization, because I think it can affect your outcome.
It can, yes, but we run this enough times that you can see the shaded area here is
I see.
Is a standard error of the mean across our training runs. So you can see that it's not too bad. Well, you know, I should qualify that. We know from some other works that variance may be so high that just running with 5 or 10 runs may vastly underestimate the variance. And some works show that we need maybe 100 or more runs to really capture the variance across runs. So we did not do that. This is too computationally intensive.
Right, but it's kind of, I think this is a shared concern in RL, right? That's why I asked. Yeah, I was looking mostly in your first graph, and I guess I missed those lines that are your area, the region of variance. But yeah, it shows that statistically the differences are significant, yet you can see that sometimes you have some crossovers.
That is true. So in the left 3 columns, you actually see all 5 runs. And on the right column, you see in shaded their standard error of the mean.
Mm-hmm. Thanks.
Now, another objection could be that, well, when we have an ensemble, we have effectively a larger model, right? So if we have 5 ensemble members, which is what we had in these experiments, it's effectively a 5 times larger neural network running in parallel. And also because we're updating each of these members in every mini batch, we're updating 5 times as frequently. So you could ask, well, are these the reasons that we outperform? Well, no. So the baseline was really very well tuned, and just having a larger network or having more frequent updates does not help the baseline, as these show. And I'm not going to dive into all the details there, but that's not the reason, right? So we can ask ourselves, okay, so what is the reason, right? This is sort of simple enough to try to understand what's going on. And it's deceptively tricky to really understand what's going on. So we have some notion of what might not be the reason that this works, but it points to deeper interactions between the components that must be studied in order to really understand what's going on. And we don't have the answer, but we do have an indication of how deep this runs. So let's talk about that briefly. So the idea is that we reduce the variance if we have partially correlated models, right? So the less correlated they are, the more averaging reduces their variance, and therefore reduces the update bias through the Jensen gap. And then maybe we won't need the target network, which further reduces the update bias. But the important thing is to keep our ensemble uncorrelated, or as uncorrelated as possible. So notice that here we had no explicit attempt to maintain diversity, right? There's some ensemble methods where they try for the ensemble members to be as different as possible. That's not what we do here. We're really just trying for the ensemble members to capture the real distribution of the models given the data. But it is important for that to keep independent samples, although we do sample from the same replay buffer. So it's not as uncorrelated as it could be on really different runs of the method. Turns out that's good enough, even though they also share the same target function. I'm going to skip this slide. It kind of illustrates how the ensemble diversity is lost throughout the training as the ensemble becomes more trained and agrees on what the target value is. I want to instead talk a little bit about why this is so confusing that this works well. Let's start with a linear function approximation, which a lot of people use for theoretical reinforcement to study what happens theoretically in these algorithms. Turns out that this is not powerful enough to capture what's going on here. So if we have a linear function approximation of our Q value, which by the way includes the tabular case as a special case, then MeanQ is essentially, after some algebra, it's essentially learning only the mean value of the parameters. So we only ever use the mean value of the parameters here, never any other functional of the ensemble. And so it's really the same as just Q-learning with the mean theta, with the mean parameter. So this would not be any different than just standard Q-learning, would not give us any benefit if our function approximation is linear. So that's not enough to even study this, the benefit of this method. It must happen with nonlinear parameterization, and that's somehow helpful when you do that averaging. Let's also talk about the independent sampling. What happens if we have the same sample for every member of the ensemble? So the same experience trains every member of the ensemble. Well, intuitively, it can hurt our diversity, but let's dive a little bit deeper into what might be happening here. So let's make a simplifying assumption. Let's assume that our value, the value of the network, the Q value that it predicts, is approximately roughly uncorrelated with the gradients. That is roughly happening in a lot of representations that we look at. And if that's the case, then again, we see that our mean Q update only updates the mean of the parameter, even when it's nonlinear, as long as this decorrelation happens. So again, this would not work. This would not give us any benefit on top of just Q learning with the average theta. So really what comes out of these equations is that we must have nonlinearity, and we must have resampling for individual ensemble members jointly in order to see the benefits of MeanQ. What is the interaction between these? We're not entirely sure. We think it has something to do with, you can sort of view this as dropout, right? As every member of the mini batch, you train a different ensemble member. It's like dropping out the others, but it's dropout that is very structured. It's not just a dropout layer, but it's a more structured dropout network. And somehow that is very powerful. We're not entirely sure why. So this is an ongoing investigation. And we think that there's a lot more to do this, just to underline how much in theoretical RL there are basic things that we don't understand, and a lot of benefits to gain by really understanding these seemingly simple concepts. So the takeaway from this part, I want to leave some time for the other part where we talk about multi-agent, is that variance reduction through ensemble mean can really go a long way in reinforcement learning. We need to tread a really careful line between sample efficiency and ensemble decorrelation. And we need better theory to understand what's going on. So I can pause here for more questions before moving to the second part.
Any questions? So I have a question. So when you have multiple agents, have you tried to see if they, I'm assuming your experiments, they start to learn at the same time, but if they start to learn at different times, is it possible that the new ones that are starting to learn to kind of learn some skills from the ones that have already learned something, so that they do not start from scratch?
That's an interesting question. Yeah, so there's a lot of work in reinforcement learning, also from our lab, about avoiding tabula rasa learning, where you don't learn from scratch new tasks. I don't quite see how it would work in this context, because keeping the diversity of the ensemble is really key. So if you initialize one ensemble member from another, that kind of goes against that, right? That kind of reuses all the data that went into the first member, reuses it for the second, and you really collapse the diversity of the ensemble, and now averaging them really gives you no benefit. So in this specific case, I don't see how that would work, unless maybe you add another term that encourages the diversity of the ensemble. The worry is that an explicit term like that may overdo it, right? May actually create ensembles that are different, diverse, just just to spite, not in a natural way that captures the variance of learning from the data. And so we don't want to have that either.
Thank you.
Great question. So let's talk about the multi-agent case. And the connection between the two parts is kind of loose, population-based. So we're going to talk about population-based methods for zero-sum games. Zero-sum games are the case where now to the same environment there joins another agent, an adversary, and it's zero-sum in the sense, yeah, a lot of real cases are like that. Real games, for what they are worth, robust RL formulations where there's an adversary that sets difficult conditions for the agent to cope with to make it learn better and more robustly. And so the two agents take actions, and the reward of the one is the penalty of the other, right? So the negative of the reward of the other. And this can be partially observable. That makes it really challenging, right? So when these agents don't necessarily see the state of the environment, they see a noisy observation of that state. When they do see the environment, that's called the Markov game. And that's generally easier to solve. Of course, there's a question of scaling to large games, but when it's partially observable, that generalization is really hard. Even partially observable single agent environments are hard to solve. What do we do when we have an adversary? So one thing that people do very often is just independent reinforcement learning of the two agents, one in the context of the other. So some terminology, best response is when one agent is optimizing its policy with the other player fixed. And Nash equilibrium is when neither player wants to switch. They are both best responding to the other. And self-play is just switching each agent to its best response or training it towards its best response in the context of the other, the other's last policy. So they're kind of doing it concurrently at the same time, and it looks something like this. If this is the history of player two's policies with the oldest at the bottom, the newest at the top, player one is really just best responding to player two's last policy. You see in blue here. So the weight of the policies in player two's history, and all the weight is on the latest one. And similarly, for player two, best responding to player one, just the last policy. And that's called self-play. There's no convergence guarantees. In large games, it may work well. Definitely in games of skill, where it's really just about improving your skill against an opponent. But in games where you need to be strategic, this may not converge, and in fact, often does not converge. In simple games like rock, paper, scissors, this does not converge. One way to see that this does not converge is to understand that a player must be stochastic in these kind of games, so that the other player best responding to myself cannot exploit the specific choice of my policy, right? Cannot predict what I'm going to do and just exploit that. So I need to be stochastic, obfuscate my information a little bit, hide information. And so this method is not stochastic and therefore cannot be optimal. An improvement is fictitious play, where each agent best responds to the other's average policy, which is just a flat average of the history of the other player's policies. And this can provably converge. And but you know, the downside here is that we average all policies regardless of how bad they were, how old they were. Maybe there are some really not very good policies here. The algorithm says throw them in, and it's obviously suboptimal, but it does guarantee to converge. And there's a counterpart of this in large games. In contrast, we consider algorithms called double oracle. Double oracle is where we focus our averaging on better policies, and it works something like this. There's two oracles, one for finding the Nash equilibrium of the restricted game, restricted to only the past best responses, the past policies that the agents had. So look at the past policies for agent one, past policies for agent two, look at the game restricted to those possibilities, solve it, find the Nash equilibrium, and that is your restricted Nash equilibrium. And then every player best responds to the other's restricted Nash equilibrium. So if we had an oracle for solving this small game and an oracle for best response, that's the double oracle, and that's the algorithm, right? So you can think of every player responding to an average of past policies of the other player, which average? The one that is best for this restricted game. And the same for the other player. Okay, so bad policies are naturally down-weighted here just because they're not really appearing very often in the best play against this population. So that's a double oracle algorithm, and it's guaranteed to converge. And now we can ask, how do these algorithms generalize to large dynamical environments, large games? Self-play scales very nicely, but there's no guarantees. Fictitious play, there's an algorithm called NFSP that scales nicely, but is very unreliable, very unstable. Double oracle, there's an extension called PSRO that has nice guarantees, but only asymptotically, and the games can grow very large. So we really want to take this PSRO and be a lot more efficient when we have large games. Let's talk about the convergence properties here. So PSRO is guaranteed to converge once all the policies are added to the population. That's almost not saying anything, right? Once all the policies are added, now I play the restricted game. The restricted game is actually the full game. So yeah, I solve it and I'm done, right? So, but that's not saying much, because it can be exponentially in the number of information states, right? So when you have a temporally extended game, right, with multiple steps, multiple turns in the game, the number of information states can grow exponentially, right, just in the horizon. That is called sometimes the curse of history. And then the number of policies grows exponentially in that. So it's doubly exponential. And empirically, this does happen. Here's even just a very small game, this double rock, paper, scissors, where we find that we often need all policies to be added to the population. So both from a theoretical point of view and from some experiments, we see that this algorithm is very inefficient. So here's what we propose. We call this extensive form double oracle, XDO for short. And it works like this. The oracle that finds best responses is using reinforcement learning against the restricted Nash equilibrium of the restricted game. That's the same as in PSRO. However, the restricted game is different. So the restricted Nash equilibrium that we find in existing populations, that's different. And the difference is that we're going to keep the structure of the game, the sequential structure of the game that has turns, has the agents taking turns. That's sometimes called the extensive form of the game. So in action in our restricted game is choosing a population best response to take the action. But whereas PSRO is choosing a best response for the entire episode, right? So mixing at the beginning of an episode and using a past population best response for the entire episode, XDO chooses a best response to take an action in every step and mixes again and again in every step. Right? So instead of just mixing at the beginning of the game, we mix again and again in every step. And that is equivalent mathematically to a restricted game where the actions that we can take in every state are all the actions that any past policy has ever taken in this state. And right, by having this sort of decomposition over states, temporally extended, we sort of obfuscate our future actions, right? So we're not as predictable. So now we solve the restricted game using any solver, maybe NFSP. And that's worth it while our restricted game is still much smaller than the full game. And so we can see some results for a very simple game here. We have amazing results. in orange, outperforming baselines in green and blue. For other games, the benefits may not be as large, but often they are very significant. So it really depends on the structure of the game. And the question that needs to be asked, not always easy to answer, is do we really need to mix our policies again and again throughout the game? Or is mixing at the beginning already hiding enough information that it cannot be exploited for the remainder of the game? It's kind of like related to system identification and the question of, can I, through interaction with the system, inside the system, not in learning time, but in execution time, identify which system I'm working within. And now we're asking the same question for an opponent agent. Can I identify throughout play which of the policies, past policies of my opponent it's currently using in this episode? If I can do that very quickly, now I'm going to exploit that policy for the duration of the episode. But if that opponent gets to mix its policy in every step, now that prediction is no longer possible, and it's a much better opponent, and playing against and trying to beat the better opponent makes me better, and so gets me to improve faster, and that's what we see. Some theoretical properties. So XDO is actually guaranteed to converge to a Nash equilibrium in a number of iterations that is linear in the number of information states, in the number of possible belief states of the agents, joint belief state of the agents. Remember, for PSRO, it was exponential in this number. So we get an exponential speed up in the best known guarantees. One drawback of XDO is that our restricted gain grows faster. We're adding, every time we add another policy, best response to our population, we're adding all the actions that it takes in any state, right? So we may add a lot of actions to a lot of states if those actions were never taken by any other population policy. And that can grow the restricted gain maybe exponentially fast. So it's a trade-off. Iterations become harder to solve faster than in PSRO. So the number of iterations is not the only thing that matters. There's a trade-off between the number of iterations and the fact that each one is getting harder and harder to solve much faster. So why is the balance in XDO's favor? Well, sometimes it's not in every game it is, but the intuition for why it is when it is that XDO allows mixing BRs in every step. And intuitively, we add an exponential number of combinations, but we actually need them, right? So if we want to be able to mix, we actually need all these combinations. We have a succinct representation of them, but we may need them conceptually to be able to hide information from the opponent and be a stronger opponent to beat, and therefore cause the entire system to improve faster. In the interest of time, I want to leave some time for questions. I'm going to skip this. This is another result that we recently published. I'm just going to skip it for now. And skip to the takeaways. So generally, agents improve faster when they train against good opponent policies. In self-play, this may not be the case. In independent reinforcement learning, this may not be the case because maybe my opponent is not so good now, so I exploit it, but in a way that it is itself very exploitable. And now we're in a cycle of just being very exploitable and finding silly mistakes for the other while being silly ourselves. So we really need game theoretic guarantees for improving. And generally speaking, just looking at the last policy is not as good as looking at the average policy, which is not as good as looking at the best mix, because this is just an average mix, uniform mix. And that's not as good as looking at the best sequential mix, which is not a really good opponent. And this is for that paper that I did not have time to discuss. So I'll pause here for any questions and thank my collaborators. And thank you for listening.
Thank you for your presentation. Any final questions? Okay, it looks like there's no question. Thank you again, and I'll meet you soon. And I think we can end this session.
Thank you.
Bye.